Welcome to Advanced Linear Algebra. Today we are going to explore one of the most elegant and powerful ideas in mathematics, known as dual spaces. If you have ever wondered how we mathematically represent the act of measuring a vector rather than just the vector itself, you are in the exact right place. Let us dive in and build this intuition from the ground up. Before we look at any equations, let us build our intuition. Imagine you are at a grocery store. Your shopping cart contains a specific amount of different items, like 3 apples and 2 bananas. In linear algebra, this cart represents a standard vector holding a list of quantities. Now, think about the price scanner at the checkout. The scanner reads your quantities, applies a specific price to each item, and spits out a single final bill. In this analogy, the price scanner acts as a linear functional. The collection of all possible pricing schemes the store could ever use forms what we call the dual space. Now that we understand the analogy, let us formalize this mathematically. We start with a standard vector space, which we call V. We also have a field, F, which provides the numbers we use for scaling, like real or complex numbers. A linear functional is a special function that takes a vector from V as its input and outputs a single scalar number from F. Crucially, this function must be linear, meaning it respects vector addition and scalar multiplication. The dual space, denoted as V star, is simply the set of all possible linear functionals that can be applied to V. It is a space of functions. To see how this works in practice, let us define a specific linear functional. We will work in the standard two-dimensional plane. Our formula here defines a functional called f. The rule for this functional is to take 4 times the first coordinate, x, and subtract the second coordinate, y. Think of this as our specific pricing scheme from the grocery store analogy. If you increase the x-coordinate, the final scalar output increases by 4 times that amount. If you increase the y-coordinate, the output decreases. This simple algebraic rule is our measuring tool, ready to collapse any two-dimensional vector into a single number. Now that we have our measuring tool, let us use it on a concrete example. We are given a specific vector v with coordinates 2 and 3, and we want to evaluate our functional f for this vector. The process is straightforward substitution. We take the first coordinate of our vector, which is 2, and plug it into the x position of our rule. We take the second coordinate, 3, and plug it into the y position. This translates our abstract functional rule into a simple arithmetic problem. We are now ready to calculate the final scalar value. Continuing with our calculation, we perform the basic arithmetic. Multiplying 4 by 2 gives us 8, while the 3 remains unchanged. Finally, we subtract 3 from 8 to arrive at our final answer of 5. This single number, 5, is the scalar output of the functional. Returning to our analogy, if the vector was a shopping cart with 2 apples and 3 bananas, our functional was a pricing rule that charged $4 per apple and gave a $1 discount per banana. The final bill for the entire cart is exactly $5. Let us look at what this evaluation actually means visually. On this graph, you can see our standard two-dimensional space. The solid black arrow represents our vector v, pointing to the coordinates 2 and 3. The dashed diagonal lines represent our linear functional. Each dashed line is a contour where the functional evaluates to a specific constant number. Notice how the tip of our vector lands exactly on the dashed line labeled f equals 5. This diagram beautifully illustrates how a dual vector acts as a set of parallel measuring lines, assigning a single number to any standard vector that crosses them. Now that we have seen a single functional in action, we must ask, how do these functionals interact with each other? Remember, we call the dual space a true vector space. For that to be true, the objects inside it, the functionals themselves, must follow the standard rules of vector spaces. Specifically, we must be able to add two linear functionals together to create a valid new functional. We must also be able to multiply a functional by a scalar, stretching or shrinking our measuring tool without distorting its linear nature. Let us look at the exact formulas for these operations. Here is the formal rule for adding two functionals. We define the addition of two functionals, f and g, by observing how they act on a generic vector v. The formula tells us that applying the combined function, f plus g, to a vector is mathematically identical to evaluating f and g separately and then adding their scalar results together. Conceptually, this means if you have two different pricing schemes, combining them into a single master scheme gives the exact same final bill as calculating the two bills separately and adding them up. It is perfectly consistent. Next, we have the rule for scalar multiplication. If we multiply a functional f by a constant number c, we create a new scaled functional. The formula shows that applying this scaled functional to a vector v is exactly the same as applying the original functional to v, and then multiplying the final numerical answer by c. If the scalar c increases, the final numerical output increases by that exact multiple. This ensures that stretching our mathematical measuring tool scales the final measurement by the exact same amount, preserving the linear geometry of the space. Let us put these operations to the test with a second example. We will demonstrate why the dual space is a vector space by actually adding and scaling two different functionals together. We want to create a brand new functional called h by taking 3 times a functional f and subtracting a functional g. We are given the rule that f is x plus y and g is simply 2x. Our first step is to substitute the specific algebraic rules into our equation for h. We place the rules inside parentheses to ensure we distribute our scalars correctly in the next step. Continuing our derivation, we distribute the scalar multiplier of 3 across the x and y terms. This gives us 3x plus 3y minus 2x. By combining the positive 3x and the negative 2x, we arrive at the simplified rule for our new functional, x plus 3y. We have successfully built a complex measuring tool out of two simpler ones. Finally, we test this new tool by evaluating it at the vector 1, 4. We substitute 1 for x and 4 for y. 1 plus 12 gives us a final scalar result of 13. This proves that combinations of functionals function perfectly to produce reliable scalar numbers. You might be wondering why we go through the trouble of defining these new spaces. Understanding dual spaces is absolutely critical because it allows mathematicians and physicists to separate an object from the measurement of that object. In quantum mechanics, physical states are represented by standard vectors, while the act of measuring those states is represented by dual vectors, famously known as bracket notation. Furthermore, in computer science, machine learning algorithms like support vector machines use dual spaces to find the optimal boundaries between different categories of data. Without dual spaces, our ability to mathematically model quantum observations and complex optimizations would completely collapse. Let us summarize the key takeaways from our exploration of dual spaces. First, remember that a dual space is simply a collection of all the linear measuring tools, called functionals, for a specific vector space. While standard vectors represent physical quantities or directions, dual vectors represent the mathematical rules for assigning a single number to those quantities. Because these measuring rules can be added and scaled, they form a vector space of their own. By treating measurements as vectors, you have unlocked a powerful new perspective that is essential for advanced mathematics and modern physics. You have covered the full topic brilliantly.